Hello, students. This is lecture number 4 in the series of lectures on the topic of indexing. And today we're going to talk about multidimensional indexing. Well, what is multidimensional indexing? I think it would be a good idea to look at a query that we talked about in the previous lecture. So here, still remember we got a relation, and this relation has a number of attributes, among which there are two attributes, one named A and the other one named B. So this is the SQL query we talked about. And in this query, as you can see, we've got two range conditions here. So that is the first one. This is essentially saying, the A value must fall into this range. So here, this is the B, another range condition on the attribute B. Okay, so you can see this is the range. Um, if you look at this in a graphical manner, um, so let's look at this two-dimensional space. So this is dimension A and dimension B. Okay, so you can see in terms of A and B, every tuple can be represented as a point, right? So this point, this x coordinate represents the A value of the tuple, and the y coordinate represents the B value. Okay, so if you look at this range condition, essentially this is saying I want to find all the tuples in this orange rectangle. And likewise, if you want to retrieve all the tuples satisfying this range condition, and then essentially you're looking for all the points that are inside this range rectangle. Okay. However, here the query says n, so a point has to satisfy both the A condition and also the B condition at the same time. So you can see, geometrically speaking, this is equivalent to saying you want to retrieve all the points that fall into this intersection. Okay, so basically this is the only area we're interested in. Okay. I don't know if you still remember this, but in the previous lecture, we talked about one strategy to use two B trees to process this query. Okay, we had a B tree on A, and we had another one on B, and then we used the first B tree to retrieve all the tuple IDs in this um, orange rectangle, and then we use the other B tree to retrieve all the tuple IDs. I should have said the IDs of all the tuples that fall into this orange rectangle, and then we perform the intersection of the tuple IDs, and that was how we got this area. Okay. Well, if you think about it, this is basically saying we use two one-dimensional um, structures. Sorry, yeah, that was interestingly ambiguous. So we use two data structures that are one-dimensional to process this two-dimensional query. Okay, so let me repeat. This B tree. This is actually a one-dimensional data structure, and we put together two such data structures to process this two-dimensional query. Okay, so this is not ideal intuitively, because we retrieve a lot of unnecessary points, right? You can see the points that are in these regions are really unnecessary. Okay. Um, so this is the consequence of basically a mismatch in the dimensionality, right? Because B trees are one dimensional. When you perform search using a B tree, and then essentially you can only focus on one dimension. So, and then you have to sacrifice, right? You have to do an overkill by retrieving a superset of what you eventually need, right? Because simply the first B tree is blind to whatever happens along the other dimension, right? On the other hand, the query is two-dimensional. So there is a misalignment in terms of dimensionality. So now this generates a very interesting question. Is it possible to design a data structure which is inherently multidimensional? Okay. And can we obtain a data structure that will allow us to go directly to this region without having to retrieve any unnecessary points? Okay. All right, so this is the question I asked on the previous slide. Um, so something very important here is the word efficient. Okay, so what do we mean by answer queries efficiently, right? So far, this is fuzzy. Okay. Now, speaking about this, let's think about what the B tree is capable of doing. So let's imagine that let's recall that the B tree uses a linear number of blocks. Okay, so once again, n over lambda is the linear number rather than n. Still remember, right? Lambda is the block size. Okay, so n over lambda is the smallest number of blocks that you will need in order to store n values up to a constant factor. Okay, so in the disk environment, we measure space by how many blocks you use rather than how many words you use, right? So this n over lambda is the best you can do, basically, right? So a data structure is set to use the linear amount of space if its space complexity is n over lambda. Okay. Right. So the B tree is such a data structure, and it's able to process any range query and um, this IO cost with this IO bound. So if you look at these two terms, this is the height of the tree, and also this is how many IOs you have to read in order to report all the tuples in the result. Okay, so if we have k tuples in the result satisfying this range condition, and then you have to report k values, and each block can contain at the order of lambda values, right, up to a certain constant. And therefore, no matter what, you will have to read k over lambda blocks just to find the k points that you want to report, right? So if you think about it, this term, we usually refer to this term as the linear output cost, because no matter what data structure you'll be using, you will always have to pay such a cost. Okay, so other than this linear cost, you can see that the B tree is super efficient. So you only have this logarithmic term there. And now remember the base of the logarithm is lambda, and that's a pretty big number in practice at the order of hundreds, I would say. So this log base lambda of n is something quite small. Okay, so this is what we mean by efficiently. Okay, so we want to achieve this query bound. Very naturally, we ask the question in two-dimensional space, or even three-dimensional, four-dimensional, is it possible to achieve this bound, and also with the linear space consumption? Okay, can we attain the same performance guarantees when more than one dimension is involved? Okay. All right. The short answer is no, unfortunately. Okay. We won't go into this a lot, but later I'm going to explain to you, what this means. Intuitively, when the dimensionality goes up, the problem of range reporting becomes more and more challenging. Okay, so the amount of space that you will need in order to achieve a query bound like this will be super linear. Okay, will be more than linear. Okay. However, there are some interesting exceptions in practice, and this is what we're going to talk about next. So there are certain situations, basically some corner situations, but these situations are not completely irrelevant and useless in practice. So in certain situations, it is possible to use um, just a B tree to handle multidimensional queries and still achieving the linear space and this wonderful query bound. But I emphasize, these are exceptional cases, and this is what we're going to talk about next as fake multidimensional queries. Okay. So as you will see, the B tree will be able to handle certain multidimensional queries. However, in essence, you will see these queries are not genuinely multidimensional, right? So they appear to be multidimensional, but they are actually one-dimensional. So this is something that is quite um, um, I would say that's quite um, bizarre and that's quite counterintuitive. But on the other hand, you will see it's true in an interesting way. Okay. So before proceeding, I'd like to remind you that the B tree is not just useful. It's not useful only on integers. The B tree can be used um, to index any total order. The only thing we need about the total order is the comparison result. Okay, so I don't really care what the elements in the B tree are, the data elements, as long as you can compare them, then all is good. Okay, you can create a B tree on it. Okay, very nice. All right. So this slide defines something very important. This is the lexicographic order over the tuples of a relation. Okay. So you see a lot of math here. Um, they appear to be intimidating. So let's get some ideas from an example first, and then we go back to the definition. Okay. Um, so here you got this ABC as the schema of the relation. And here I show you 5 tuples. Okay. So these 5 tuples, they are partially sorted. Partially. So what do I mean? They are actually sorted according to A. Okay. As you go down the table, you can see that the A values they are in ascending order. Okay. This is saying, you compare 2 tuples by their A values, and if you have ties, so for example, the first tuple and the second tuple, they have a tie on A, and then you break the tie by resorting to their tuple IDs. Okay, so this 116 is placed first because, as you can imagine, the tuple ID, the ID of this tuple is smaller than the ID of the second tuple, 195. Okay. So anyway, so this is sorted according to A. And the meaning of that is you first compare 2 tuples based on their A values. And if the comparison result is immediately resolved already, then there's no more question. But if these 2 tuples, they have the same A value, and then you proceed to compare their tuple IDs, all right? And then the tuple with a smaller tuple ID should come first, okay? Interestingly, this relation is not sorted only on A. And you can also say that the relation is sorted on A and B. Okay. However, there is a sequence here. A comes first and then B. Okay. So we say the tuple ordering is in lexicographic order with respect to A and B. Okay. So what does this mean? Well, this essentially says that if I give you 2 tuples, such as 195 and 257, you first compare them based on A. Okay. If the comparison result is already clear, and then it's end of story. But if they turn out to have the same A value, sorry, let's look at these 2 tuples. If they have the same A value, and then you proceed to compare their B values, all right, and then you determine the ordering between the 2 tuples based on their B values. Okay, so you break the tie based on B value. But it's also possible for these 2 tuples to have exactly the same values on both A and B, in which case you break the tie based on tuple ID. Okay, so it's I mean the tuple ID is always the last resort, and you can um, always break the tie based on the tuple ID because no two tuples can have exactly the same ID. Okay. So in this case, we say, as I mentioned before, the tuple ordering, in another way, you can say the tuples are sorted in lexicographic order with respect to A, B. Pay attention, this is a sequence here, not a set, all right? Because it names the first attribute that you need to use for the comparison. Okay, so there is an ordering here. Okay. However, these tuples are not sorted according to A, B, C. Okay. Um, why? So you can see a counterexample, right? So for example, these two tuples, 257 and 252, right? They have the same A value, so the comparison proceeds to B, and they agree on B. They have the same value on B again. So now the comparison proceeds to C. And then you can see 257, this is 7 is actually greater than 2. So according to a lexicographic order on ABC, you would have to move 252 before 257, right? But this is not the case here. And therefore, you cannot say that these tuples are sorted according to ABC, all right? And likewise, you cannot say that these tuples are sorted with respect to BA, okay? Because, in this case, if you talk about the lexicographic order BA, and then you will have to be comparing two tuples based on their B values first, right? And then in this case, 341 will have to rank before 195, all right? But that's not the case here. So, I believe you have got a strong idea, strong intuition about the definition of this lexicographic order. Now let's go back to look at the definition more carefully, and I believe this time it should be much easier to understand. So in general, it can have a relation with the schema like this. So this schema has D attributes. Okay, so the total number of attributes is D, right? As usual, every tuple is assigned an ID by the system. Okay. All right. So when we say these tuples are sorted according to a lexicographic order with respect to these attributes, what we mean is the following. So first of all, these attributes, they are all distinct attributes. Okay. Otherwise, it's redundancy, right? I mean, why do you have to list the same attribute twice? That doesn't make any sense, right? So these attributes are distinct attributes. And also pay attention, the number of attributes does not have to be equivalent to D. In other words, you don't have to include all the attributes in this definition. All right, we saw this in the example just now. I said these tuples are sorted by A and also sorted by A, B. As you can see, I don't have to include A, B, C in the definition. Anyway, so now you have got a sequence of attributes here, and then basically the sequence determines the comparison order. Okay, so if you have two tuples, you first want to compare them based on x1, and if you already have a verdict, and then the comparison is done. But if they have the same value on x1, you proceed to compare their x2 values and so on and so forth, right? It's also possible for T1 to T2 to have exactly the same value on every single attribute, in which case you simply compare them based on the ID. So ID is always the last resort, okay? So the mathematical definition here is basically another way to say exactly the same thing, but the way that I explained it should be more intuitive, and it's also identical. Nice. All right. So this should be an easy slide. So basically, um, you have already defined a total order. So whenever you have a total order, you are able to create a B tree on it. I think by now you should have been very familiar with this. So this is essentially what the slide is talking about. I think we can try to go into this formal definition directly. So you got a relation here, and every tuple in the relation carries an ID. And here you've got a lexicographic order, and you specify this lexicographic order with respect to a sequence of attributes. Okay, and then you got a total order. And then you can create a B tree on this total order, and this is a dense index, meaning every tuple in the relation has a leaf entry in the B tree. Okay, and okay, so that's the first bullet. The second bullet basically says, since this is an index, it's not just a data structure. Okay, so it's an index. You have to store pointers from the leaf entries to the corresponding tuples. Okay, so more specifically, you have to remember the address of the block containing the corresponding tuple. Okay, so everything sounds familiar, right? So basically, this is exactly the same definition we saw in the previous lecture, except that here the total order is defined on multiple attributes rather than just one attribute. Okay, and you can also say that this definition generalizes the definition we had in the previous lecture, because in the previous lecture, the value of t was strictly one. Okay. Nice. So here, just in case that wasn't clear enough, here is an example. Here we've got ABC as the schema for the relation. And let's just say that somebody has created a dense index on AB, okay? And then this is what the index looks like, okay? Hey, let's first look at the brown blocks. I hope you still remember um, similar examples from previous lecture. So this is the file of the relation. As you can see here, the tuples are not sorted in any particular way. Definitely not sorted on A, definitely not sorted on AB. So sort of like a random order here. But if you look at the data elements in this B tree, actually it's a dense index. So you can see two things, right? First, for every tuple, you have a leaf entry corresponding to it. So for example, this one, so this is the A value and that's the B value. So you can see this is the leaf entry corresponding to the tuple. And this leaf entry holds the tuple ID, and also it holds a pointer, and this 80 is the address of the block containing this tuple. Okay, so this is a dense index. On the other hand, if you look at the leaf level, you go from left to right, and what do you see? You see that the data elements, so basically, the data elements here, right? The data elements are sorted, okay? Sorted according to the lexicographic order defined on AB. Indeed, you can see this pair is before this pair, right? Because 53 is less than 68, and 68.9 is less than 23, right? And so on and so forth. Okay, so everything should come together now, right? All these things are falling into the right place. This is really just the same definition as in a B tree. And the only thing is that the B tree is created on a total order, and this total order is the lexicographic order on AB. Okay, nice. Very good. Okay, so let's quickly generalize this concept of clustered, okay, clustered to the multidimensional case here. Basically this cluster basically says sorted, right? So it's there's no mystery here. It's when you say a relation is clustered on T attributes, I mean a sequence of T attributes, then basically saying that the tuples are sorted lexicographically with respect to this sequence. So once again, two tuples, they get compared on B1 first. If you have a tie, and then you move on to compare their values on B2 and so on and so forth, right? And eventually you break the tie based on topology, okay? And then essentially, if you look at the file of this relation, you see that the tuples in the file, they have already been sorted according to the lexicographic order. Okay, good. Still remember what a cluster index is? A cluster index is an index. Actually, you know what? I would say it in another way. If R is cluster on x1 to xt, and T is created on the same sequence, and then you can say that this T is a cluster index. All right. So once again, it's consistent with what we learned in the previous lecture. An index is clustered if the data elements in the B tree, the data elements at the leaf level, right? They are sorted in the same way as the tuples in the relation. Okay, so that's the generic definition of clustered index. Okay, so whenever the index, whenever this is not true, and then we say that this is a non-clustered index, or we can say it's a secondary uh, index. Okay, nice. All right, so finally, I get to talk about what it means by fake multidimensional queries. Okay, fake. All right. Now let's see that here we have a relation like this. And here we have created a multidimensional index. This is a B tree. It's a dense index on the lexicographic order with respect to x1 to xt. Okay, good. Now, if you have a multidimensional, condition like this, and then this is actually something that can be processed by the B tree. Okay, so let me explain again. So here you see L attributes. Okay, x1, x2 to xl. Okay, and you have one condition on every attribute here, so it appears to be multidimensional, right? However, this is such kind of condition is peculiar in the following way. Look. So first of all, you can see x1 appears here, x2 appears here, da 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 to xl, right? So this is a prefix. You see what I'm saying? This is essentially saying you have to pick a prefix of the attributes here, and you will have to specify something on every single attribute. Okay, you cannot miss out any attribute. So let's say if you do x1, but then immediately you have x3, but you don't have x2 here, and this is not okay. Okay, so I emphasize that you must take a prefix. Okay, you must take a prefix. And then you take this prefix and then look at the conditions as well. Here you've got C1 on the first attribute. That's a point query. It's a point condition on X1. It's a point condition on X2, point condition on L-1. And the only true range condition you can impose is on the last attribute. So that's XL. Okay. So to summarize, there are two conditions you have to satisfy. The first condition is that you have to take a prefix. Okay, so this prefix has length L. But of course, this L can reach T. Okay, it cannot go over T because the B tree is created on the sequence from X1 to XT, right? So this prefix length can go up to T, but it cannot go over T, all right? So you have to take a prefix. That's the first condition. The second condition says, you have to have point queries on all the attributes except for the last one. Okay, so let me repeat. You must have point query conditions on all the attributes except for the last one. For the last attribute in your prefix, you can put a range condition there. Okay, so such kind of conditions can be supported by the B tree because you are able to prove that the tuples that satisfy the whole predicate, this conjunctive predicate, they form a continuous range in the lexicographic order. Okay, so eventually you will be able to convert such a multidimensional query to just a one range query on the lexicographic order. Okay, so this is something that we will talk about in the tutorial. So it should not be too difficult for you to figure out that this is indeed true. We won't have time to talk about this in the lecture, but this is something very good for you to think about as even as an exercise. Okay, in any case, we're going to talk about this in the tutorial. So let's see some quick examples. Here I got a schema, I got a relation with ABCD, so that's the schema. And here, this dense index is created on the sequence ABC. Okay, so I emphasize ABC, right? So now here you see a bunch of multidimensional queries. So the question is, which queries can be supported by this B tree efficiently? Okay, efficiently. So what that means, you are able to achieve log base lambda of n plus k over lambda. Still remember this excellent query bound that can be guaranteed by the B tree. And this B tree is able to guarantee exactly that those bounds, exactly that query bound for two of these five queries. So now let's understand why. So first of all, we said there were two conditions, right? The first of all, it has to be a prefix. So indeed, as you can see for the first condition, this is a prefix, right? Because we're talking about just A and B. And the second condition says, if this is your prefix, and then you must put a point condition on A, and which is true here. And on B, it's up to you. You can put a point condition or you can put a range condition. Here we have a range condition. So that's all right. That's perfectly fine. Okay. Now let's look at the second bullet here. This time the prefix is ABC. Okay, the prefix is ABC. As you can see, let's make this solid here. So as you can see, A and B, we indeed have point conditions, okay, point query conditions. But on C, we also have a point query condition, which is fine, right? Because a point query condition is simply a special case of a special range query condition. Okay, so this is 30, you can think about it as 30-30, right? So there's no contradiction here, okay. That's nice. So now let's look at the next bullet and understand how come this one cannot be supported by our index here, right? So it talks about two attributes that satisfies the first condition. Okay, so far so good. But the thing is, if this is the prefix, then we will be expecting a point query condition on A, but that's not the case here. As you can see, you got a range condition on A, and this violates the second requirement. Okay, so that's why this query cannot be supported efficiently by T. Moving on, so if you look at the next one here, we're using ABC. So you are using a point query condition on A, which is good. But on the other hand, for B, this is not the last attribute in the prefix, and therefore you cannot put a range condition here. Okay, so this is not okay. All right. And finally, here for this, you are doing B and C, but that's not a prefix of the sequence ABC. Okay, so this sequence ABC matters because this is the sequence that defines the lexicographic order. Okay. All right. So this tells you what kind of multidimensional queries can be supported using a B tree. So, especially in the tutorial, actually, this is something you can think about right now. How come the B tree is able to handle these queries? As I said, you are going to convert each of these queries into a range query on the lexicographic order. Okay, so I'll leave that to you. Just some interesting brain teaser for you to think about. Okay, and I will talk about this in more detail in the tutorial. Good. All right, but these are fake multidimensional conditions, right? So how about we talk about some genuine multidimensional indexing, all right? So the B tree is for range reporting. So very naturally, we like to extend the definition of range reporting to more than one dimension. Okay, so this is quite intuitive. You are looking at a two-dimensional case here. As I said, right, every tuple can now be regarded as a two-dimensional point because you got two coordinates, you got two attributes, right? So here, an orthogonal range, this is something we call orthogonal range query. This is a two-dimensional query example. You have a rectangle. So this rectangle is axis parallel. Okay, axis parallel basically says, look, on the x dimension, you have some vertical edges here, right? On the x dimension, you got a range. So this range goes from, let's say, x1 to x2. And then on the y dimension, you also got a range. So that's y1, y2, right? So if you think about it, then basically this is a rectangle, and also it's an orthogonal rectangle. Orthogonal basically means perpendicular. Um, so it's axis parallel. Okay, so you can imagine what a three-dimensional range query would look like. So that would be sort of like a cube, right? A three-dimensional square, something like that. Okay. So in this two-dimensional case, what would be the query answer? Okay, the query answer involves 3 points, D and E and G. Okay, so these are the 3 points to be returned. Okay, good. So ideally, we would like to have a data structure that can do n over lambda blocks, just like the B tree, right? And we'll be able to answer this, two-dimensional query in so many IOs. So, this is k over lambda, and in this particular example, k is 3. Okay. So the question is whether it's possible to match these performance guarantees in two-dimensional space, right? Okay. Well, the answer is no. Okay. The answer is no. Okay. Multidimensional indexing is inherently harder than one-dimensional indexing. Okay. So if you want to have something that comes with rigorous theoretical guarantees, the answer is just forget about it. Okay. So it's not possible. So and then the natural question is, what would be possible? Okay, if you want to have rigorous guarantees. So currently, human beings are able to do the following. So if you want to guarantee the same query cost, this excellent query cost, as the B tree can do in one-dimensional space, and then the space cannot be linear. Okay, so this is the linear number of blocks, right? The linear space. So how much space will be needed? So you see, this is the linear term. Okay, so this is the term here. And there is a multiplicative factor there. Okay, so this looks fairly complicated, but if you think about it, so let me tell you one way to simplify it, right? So you can basically eliminate the denominator here. In practice, for practical values of lambda and n, this value is fairly small, okay, very small. Just think about it as a constant, and then that would leave you, this log term, okay? So this log term basically saying is like how much more? I mean, how many times more than linear space? Okay, so you can even imagine it like, how many times you have to store this data set over and over again, right? So the answer is basically log of n over lambda, right? So this is the number of blocks that you have asymptotically, right? Well, I use the word asymptotically. Probably you don't understand what that means. Anyway, if you have taken the data structure course, you understand, this big old stuff. You understand what that means. Anyway, so it's up to a constant factor. It's logarithmic of how many blocks you will need to store the data set. So even for say 1,000. Okay, so your data set is so small and it takes only 1,000 blocks, and then this is already like 10 times more. Okay, so if you have a million blocks, and then this log term is going to be something like 20. So that essentially says that the amount of space that you need will be non-linear, and the non-linear factor is going to get higher and higher as you have more blocks in your data set. Okay, so this is what people can do from a theoretical perspective. Okay, and then in practice, people don't really like such kind of guarantees because the space consumption is too big. N over lambda will be the linear space. That will be okay. That will be good. But if you say, okay, you have to spend 20 times more, and then that would put off a lot of people. Okay. So what can you do, right? Now you are at a sort of like a crossroad because if you want to go to the theory perspective, the direction of the theoretical direction, and then it will force you to use nonlinear space. So what can you do, right? So another direction is to go heuristic. Okay, go heuristic. Basically, heuristic says, okay, you know what? I will have to use linear space, and so other than that, I will not care about other theoretical guarantees. But I'll try to do my best to come up with a data structure that is reasonably good, even though I cannot prove any bounds on it. Okay, so that's basically says heuristic. So that's what heuristic means. Okay, so in the rest of the lecture, I'm going to very quickly talk about a data structure known as the R tree. This is a heuristic data structure, which means, the only thing you can prove about it is that its space consumption is linear, but there's nothing else you can prove about it. So from a theoretical perspective, you cannot say this is a beautiful data structure. However, in practice, it could be useful. At least it makes a good discussion in our lecture because, as I wrote here, it illuminates some fundamental ideas behind, how a good multidimensional index should be designed. Okay. So just want you to say the R tree is not supported by every single database system. It's supported by some databases. For example, Oracle and MySQL provide support for it. Okay, so before we talk about the R tree, one relevant concept is this minimum bounding rectangle. This basically says if I give you a set of points, as you can see the set of black points here, what will be the smallest axis parallel rectangle? Okay, axis parallel, all right, to cover all these points. So in this case, the answer is this. As you can see, you cannot shrink the rectangle any further, right? So for example, you cannot make the left edge uh, you cannot move the left edge anymore to the right because otherwise this point would not get covered. Is what I mean. So these four edges are already tight. For example, if the upper edge was here, then you'll be able to move it down, and then that case is not tight enough. But this one is already the smallest you can get, right? So that and therefore this is called the MBR, minimum bounding rectangle. Okay. Well, here I have an example for you to demonstrate what an R-tree is. So first of all, what is the data set? The data set consists of points A, B, C, D, E, all the way to I, J, K, L. Okay, you got all these points here. You have how many points? You have 11 points here, right? So no, you have 12 points here. Okay. You got 12 points, so they are A, B, C, all the way to L. Okay. All right. Now this shows you the tree. Okay. It looks like a B tree, but it's not a B tree. So let's look at the leaf nodes. You got leaf nodes U4, U5, U6, U7, and U8. So you put I and L together intuitively because I and L are close to each other. Okay, but as you can already sense, I use the term close very loosely. So in general, what do I mean by close? Well, no specific definition applies here. Okay, it's a heuristic thing. So in practice, you might want to do something like clustering so that you will put um, a cluster, let's say a small cluster into one leaf node. Yes, this is a little fuzzy and not very well defined. it makes sense only at the intuition level. But anyway, so if you put 2 points that are reasonably close, usually that will be a good idea. And it will be a bad idea, for example, for you to put I and C together because they are really far away. Anyway, so this is the principle being followed when you group the points into leaf nodes, right? So I and L, they make one leaf node, and this ADG, they also make another leaf node. As you can see, BCE, it's here, HF is here, etc., etc. Okay. And here you can see that every node contains up to 3 points. Indeed, there is also a capacity limit on how many points you can put into one node. Every node occupies a disk block, just like the B tree. Okay. So those are the elements at the leaf level, right? So now let's look at these guys, right? So these guys, they appear to be routing elements, right? So for example, E4. So what do we have? What do we have in this routing element? Okay, so in the B tree, this would be the smallest number in the subtree, right? So as I always said. However, this is in R tree, so you can no longer say the smallest. You cannot say the same thing, right? So what do you store here? Well, it stores the MBR of the leaf node. As you can see, the leaf node contains just I and L. So you store the MBR, so you put the MBR here. So this E4 is actually a rectangle. Okay, you'll be storing the rectangle. So you need 4 values to represent a rectangle, right? So you'll be storing 4 values here. So likewise, E5 will be storing this rectangle here, the red one, because that's the MBR of ADG, and you got the idea, right? So how about this E2? E2 will be the MBR of everything in the subtree. Okay, MBR. So you can see ILADG is so they are here. So at E2 you'll be storing this MBR. Okay, so that will give you an R tree. Now, why is this useful? Okay, so this is useful because the MBRs, they serve as the routing elements, and they will be able to guide your search in a meaningful way. So for example, let's say we want to answer this range query here. Eventually, we want to report D, G, and E, okay? So how does the algorithm work? Well, it starts from the root. So as you can see, it's the root here. And then you load up the root, you see 2 MBRs, right? You see this E2, and you see this E3, but you don't see anything else, right? And then obviously you have to access the subtrees. Sorry, you have to access the child node of U2 because the MBR here intersects with the query, right? So you cannot exclude the possibility that you could have points here, and therefore you have to go in and take a look. And later we'll also have to access the child node of E3 because this MBR here intersects with this query. All right, so let's look at U2, and then you load up U2 from the disk, and then you see 2 MBRs there, E4 is here, and E5 is there, okay? So the good news is for E4, you can see it's disjoint with the query rectangle, and therefore you can forget about the subtree of this E4. Okay, so now you can achieve some pruning effect, right? Some pruning effect. And for E5, on the other hand, you still have to access it. Okay, so if you follow this principle, and then you know that on the other side, U3, you load up this node, and you see 3 rectangles there, right? And among those 3, only the rectangle E6 intersects with the query. So basically, you end up accessing U1, U2, U3, and then U5, and finally U6. Okay, so you'll be accessing a part of the tree to answer this range query. Okay, but as I said, this is a heuristic structure, and no interesting theoretical guarantees can be established about it. Okay. So I mentioned a little bit about the principle behind designing a multidimensional index, right? So this is basically what the archery is using, right? So the principle being illustrated here is that you would like to group the points using some sort of clustering ideas so that the NBRs can be made small, right? So this is something very important. So this basically differentiates a good archery from a bad archery, okay? Um, yes. All right, so that concludes this short lecture. This lecture, together with the previous one, will constitute the contents the contents of this week. Okay. All right, so that's everything I have, and then I will see you in the classroom. Okay. Bye bye. Take care.